Thanks, Alex, for the introduction, and I welcome all of you to this webinar. I'm not that used to go for webinars, but I try my very best, and I hope you will enjoy it. So the presentation is on MICRESS, a commercial software developed and maintained by a non-profit organization, and the non-profit organization is called Access. I'm coming to that a little bit later. But let me first introduce myself. So during a webinar, people cannot see each other unless they spend bandwidth for the video, which I didn't want to do. So the rough stations in my life has been a diploma in particle physics in 1985. And lately in this year, I already joined the Access EV, which was not even existing at that time. But I'm still with them now as a senior scientist. In 1985, I was still a little bit a junior. So I did my PhD in the area of high temperature superconductors, and one of the areas I was looking for was to understand microstructure formation in these kind of materials, and that was the beginning of my work on the MICRESS theory and the MICRESS code development, and later on the MICRESS sales. So currently, I have been, just until end of last year, I've been the agent for thermocalc software in Germany, and I'm doing all the global marketing for our MICRESS code. I'm a member of several associations, and especially in the area of ICME, I'm a member of several expert groups, and I even edited a book on software solutions for ICME. So as mentioned, I'm currently with Access EV, and this is a private and non-profit research institute which is associated with the RWTH university. So we are legally and financially self-supporting, and we are not supported by the university, but we are registered, or we are looked at as an institute at the university, but not a university institute. We have been founded in 1986 as a spin-off from the Foundry Institute of the RWTH Aachen, which at that time was a leading institute in the area of microgravity research, especially on solidification. So the director of the Foundry Institute at that time was Peter Sam, and he was the scientific coordinator of the entire German space lab missions called D1 and D2. And in the wake of this, the Access was founded as a so-called Center of Excellence for solidification research in microgravity, and the original name was Aachen Center for Solidification in Space. But already during the period of our foundation in 1986, there was the Challenger disaster in early '86, and so we have been grounded with our research for almost 5 years, and in that sense we started to redirect our research towards general material science and processing, with a focus on alloy solidification and casting, as we originate from the Foundry Institute. Meanwhile, we have extended our activities also to heat treatments and welding processes, but still anything related to metals and alloys is of interest to us. Our employees are 35 researchers, and the specific situation at our place in comparison with university institutes is that we have a very skilled workforce. So most of these 35 researchers are already with the company since more than 20 years. Almost all of them hold a PhD. And it's a very wide variety of skills we have. So we've got mathematicians, physicists, chemists, mechanical engineers, foundry engineers, informatics people, and so on. So as we are a non-profit research institute, we have to fund some money to do our work, and 50% of our funding comes by public research funds like German Research Society or European Commission and national grants and so on. And the other 50% we earn by industrial contracts. These contracts essentially come from aerospace, automotive, power engineering, and so on. And the customers are both OEMs and also suppliers and end users. We've got 3 different locations in the meantime. So originally, when we were founded in 1986, we had the entire first floor in the building of the Foundry Institute, and this is still the case. So we still have this entire floor, and this is the building of the Foundry Institute of the university. We share the second floor with the Foundry Institute, and we've got almost all our analytical facilities here in the first floor. About 2000, we went for another premise at the Jülicher Straße, so it's the same city, where we rented a real estate of 1,200 square meters roughly, and the scope here was to develop casting process at the production scale level. So we've got an infrastructure in this building with a power supply of 10 megawatts and cooling facility. So this allows to operate industrial scale casting facilities and to do parameter variations in that area. And the typical procedure of an agreement with an industrial company is that we get one of their production machines and then do experimental trials to optimize the production parameters and to test the facility and so on. And then later on the machine is taken by the industrial customer and brought to its own production site facilities. About 11 years later, we even rented 2 more industrial halls on the same premise. So you see the white hall here in the back, and there are 2 more halls which we rented recently and where we do production of products, especially on titanium aluminides. I'll show you later. So the expertise of our company, of our institute, or of our association is essentially in the real life, in the real world. So this is the upper level, and in the virtual world, this is the lower level. So starting from the fundamentals of solidification, we still do some sort of microgravity experiments, but that covers perhaps 5% of our activities. But in the fundamental material science, we look for computational thermodynamics, so we develop specific thermodynamic databases. We look at phase transformation kinetics, and we look at fundamentals of solidification using so-called transparent organic analog systems, but also metallic alloys. And we do materials characterization. I come to that later in another slide. In the area of process technology, our expertise, our main expertise is of titanium and titanium alloys, and especially so-called gamma titanium aluminides, where we generated a process technology with on investment casting, using centrifugal investment casting. And the idea is to produce, not only the idea, but we produce turbine blades and other turbo machinery from titanium aluminides, but we also have a lot of work on other materials. So in the area of simulations, we developed a code called StarCast. So that's a combination of the former StarCC Plus being sold by CD Adapco and a software called CAST, like computer-aided solidification technologies, which has been developed by ourselves. And there was a joint venture with CD Adapco. But meanwhile, this code has been sold, or CD Adapco has been sold to Siemens PLM, and we now only use that code and do not further develop it. So using that code, we do process scale simulation like computational fluid dynamics. So this code is especially useful for multi-phase flow, so including, for example, also gas bubbles and so on. And we generate mold filling and solidification, and in a special sub-branch there's also the way to handle stresses and strains during solidification and so on. The code I'm going to talk a little bit more about now in this session is called MICRESS. That's the microstructure simulation, microstructure evolution simulation software. It's based on the multiphase-field model, and it handles multi-component alloys during solidification, heat treatment, welding, and so on. And the area, our business area here, is both software development and also sales, and also consultancy in this area. So these are some impressions. So this is the shell mold development for these different casting processes. Here you see the applications of the ScarCast code, where we do high pressure die casting, investment casting, also additive manufacturing, sand casting, crystallization of solar silicon, and many others. The MICRESS I'm going to show you a little bit more. We can have grain structures and also handle some fluid flow and so on, so more on this later. Interesting is that we also, in the area of development of new alloys and in the fundamentals of materials, we develop new materials based on titanium and titanium aluminides. That has been our core business since years. Meanwhile, we also go for other types of intermetallics like iron aluminides, and traditionally we serve superalloys, aluminum alloy communities, but also we generate high entropy alloys and investigate how they can be optimized and be brought into practical applications. The business activities we have at the Foundry Institute in the Inselstrasse in the second floor I mentioned, they comprise light microscopy, so polarized light microscopy, SEM, SEM EDX, SEM EBSD, and cross-beam FIB. So that especially is interesting in the area of characterization of 3D microstructures. We also have different ways to do X-ray tomography and X-ray characterization. So we've got a large chamber X-ray computer tomograph, which allows investigating even parts which have, let's say, 0.5 meter of size or so. Then we've got 3D scanning devices which allow to define outer shape of cast products and geometrical accuracy, compare it with experimental data and with 3D data sets. So the overall message I want to convey you, and this is a little bit important in view of probably of our success of the MICRESS software, we are not a software company, or let's better say we are not only a software company. So all the experience and the development of the MICRESS always is something like a co-evolution of experimental facilities, experimental expertise, and also the new functionalities in the code, and see whether they are true and whether they work out correctly and so on. So we have a permanent validation of all our simulations along with our experimental efforts we have. So now let's come to MICRESS, which shall be now a story of a commercial software developed by a non-profit organization. So I've got a little bit an outline here. I will shortly start with this MICRESS, having the initial idea and the theory, and a little describe that continuous development over the last 20 years. And in the very end, I will talk a little bit about the fun and also about the pain of going commercial, and perhaps that may help you in making own decisions in that area. So in the 1986, when I came to the Foundry Institute, essentially all thermodynamics were based on binary alloy phase diagrams being compiled into booklets, and if one wanted to get liquidus temperature of a complex alloy system, that was almost impossible. But that was also the time when there was the development of the so-called CALFAT method, where the people started to do computational thermodynamics and to generate thermodynamic databases, and that was the big story we needed in order to start the development of MICRESS, because if you want to describe the evolution of a microstructure, the minimum thing you need to know is when phases are stable at all, and that is given by the CALFAT method and the respective softwares like Thermocalc and others. On the other hand, besides the theories of the phase equilibria, which essentially computational thermodynamics has no time scale and so on, so what you only can get is information about phase equilibrium. There are other theories of phase transitions, and there are many in the history. The most well known by many people is perhaps the Ginzburg-Landau theory of phase transitions. Less people will know Kahn-Hilliard and so on. And we started to become interested in the phase field method, and actually the phase field method has been first proposed by Jim Lange in 1978. This paper has never been published, it's just the private notes, but everybody accepts that this has probably been the first formal mentioning of phase field method. We came interested, so there was a publication then on phase field in 1986, and we became interested in phase field modeling when Ryo Kobayashi in 1992 published a paper on simulating 3D dendrites using the phase field method. As we were already well aware about solidification phenomena, seeing such dendrites motivated us that there might be more behind this kind of model and method about the phase field, and that it can be extended to the things which might be practically useful. The problem was that in many cases in solidification process there is not just the equilibrium between a liquid and a solid, but there is an equilibrium between two solids and a liquid, for example, in eutectic phase diagrams or in peritectic phase diagrams. So what one needs is something called multi-phase equilibria, and it took us quite a while to extend Kobayashi's and Kajinaut methods towards a multi-phase field model, which we then published in 1996. Later on, there were further development on the phase field crystal models. I'm not going to detail, but Ken Elder was the editor together with Nick Provatas on a very nice review on phase field methods in material science and engineering, which I can recommend to read. The phase field equation itself is an own area of research. We are already in this area since its early stages in 1999, when we organized the first workshop on phase field modeling in materials science, and almost all of these people are still active in that field. Then 10 years later we organized the second workshop, and where we noted that 10 years might be too long, so we decided to go for 5 years each, and alternating between Germany and the US. And so the phase field 2014 was in the US in Penn State. And the next one actually will be this month, so in 2 weeks here in Bochum. So the mechanisms of microstructure evolution as handled by MICRESS essentially are based on, first, the knowledge when a phase is stable at all, so that's determined by thermodynamics, and then we need to know, a little bit about the diffusion time scale, and in the very end we also need to know about the curvature of interfaces, and this is due to the fact that the thermodynamic equilibrium depends on local curvature. So the example all of you might know is the radius of a soap bubble, which depends on pressure, and the smaller the radius, the higher the pressure. So the message is that thermodynamic equilibria depend on local curvature, so we need some idea how to describe curvature, and especially the phase field method is meant to do so, but I do not have the time in this presentation to show all of this. That would be another hour. So actually we then published that multi-phase field concept in the 1995, 1996, and the basic idea was to handle multiple phases, and what you see here is essentially a ferrite growing into a liquid. Oops, so I've got some automatics in here. A ferrite growing into a liquid, and what you see is that these are ferrite grains, and actually this is another phase field than this one. Yeah, so each object can generate its own phase field, and this has another orientation than that one, so that's a different phase field. Then in 1999 we had the development of really of multiple phases, so ferrite, austenite, and liquid in a steel example. And about 2008 we went into the description of interdendritic precipitates being located in the interdendritic regions. All that has developed starting from the very fundamental paper in 1996, and we've got a number of other things where we can have effective numerical schemes, effective computation, how to exploit multi-ternary extensions to the multi-phase field metals. We have to deal with self-consistency, so many things had to happen in between. The message is that even after 20 years, we sometimes have something like a breakthrough development based on all what we did before. So nowadays, these microsimulations can be applied to technical alloy grades. So we've got real steel components, cast iron, superalloys with 8, 9, 10 components. Aluminum alloys pictured here, where we have, here in this case, 14 different thermodynamic phases being described. Magnesium alloys, solders. So essentially we can cover anything related to metals and alloys and to their solidification, and later on also to heat treatment and welding processes, for example. We can do that not only in 2D but also in 3D. So this is a dendrite array in a superalloy with some titanium carbonitrides ahead of the solid-liquid interface. This is an array of magnesium alloys where you see the hexagonal symmetry of the magnesium dendrites. Here's some fluid flow through a dendrite network, and what you see up here is a so-called aluminum silicon eutectic, where we had studied the effect of strontium refinement on the eutectic structures. We meanwhile managed to pop up at several cover pages of international and national journals, and that's quite a nice story. And the overall development of MICRESS can be summarized a little bit with this graph. It's already 3 years old now. So the basis is that multi-phase field model, which we published in 1996, and then we have different branches. So we started to go for going commercial about 2003. 2002 had the first sale in 2003, and the current state is that we have more than 100 sites in 18 countries in 2016. Meanwhile, that's even bigger, that number. Yeah? Then we had the applications to solidifications, later on to heat treatment, soldering, welding, and there's even patents which have been generated based on the results of simulations. In the area of research, MICRESS has served as the basis for what we know, more than 15 PhD dissertations, and has been used in more than 100 publications. In terms of scientific networking and people, we generated the first international workshop in 1999, and also the second one in 2009, and the one in 2014. And out of our group, meanwhile, a lot of professors emerged, like Britta Nessler, who won the Leibniz Prize 2 years ago, and also Ingo Steinbach, who is with the ICAMS in Bochum, meanwhile. Niels Warnken is a lecturer in Birmingham, and so on. The recent developments is that we start to do coupling with fluid flow, so we investigate, for example, the permeability of dendrite networks in 3D flow situations. We couple the code with elastic stresses in order to describe things like rafting and superalloys. That's actually done by some of our customers. We start to link with simulation codes called crystal plasticity, which allow the description of deformation processes, and I can show you a result here where we have a crystal plasticity code, and which switches now to a phase field code to the MICRESS for the recrystallization modeling. We also try to not only to work on microstructure evolution and description of microstructures, but we also go for the determination of effective properties from these kind of microstructures. And what you see here is the derivation of the anisotropic flow curves in a dual-phased ferrite perlite line pipe steel. We started to model on a faceted growth, so that's quite interesting in terms of crack initiation, crack propagation. It's very interesting to see how sharp edges generate cracks and so on. And here you see a comparison between a 3D reconstruction of a real microstructure and a 3D simulation using MICRESS. In the last years, we also started to model joining processes, and the interesting story here is not necessarily the solidification, but it's the melting process, which is by far not yet understood. So many things are there which we can try to understand in future. Together with colleagues from other universities, we try to model failure and fatigue, so crack initiation and crack propagation. The software used here is developed by Siegfried Schmauder from the University of Stuttgart. They applied their software by now only to experimental microstructures, and we convinced them that they should go also to apply it to virtual microstructures as we show here. Increasingly, we start to take care about the information exchange with experiments like EBSD data and EDX data, optical microscope data, and all this is related to the interoperability of software tools so that we can just take our data and forward it to other codes for further processing, or on the other hand that we take data from experiments like, for example, experimental microstructures and forward them to our own tool for further evolution. The pragmatic view we have currently on a microstructure simulation environment is that we have some evolution codes like MICRESS, but also so-called DICTRA or TC Prisma and the crystal plasticity code Damask in the center of activity. So these tools evolve microstructures as a function of external boundary conditions, and in order to do so we need quite a lot of other things to show. On the one hand, we've got a pre-processing machinery, so to generate artificial microstructures. Then we need meshing tools in order to convert between voxel-type representations and FEM-type representations, and there are some codes around. Then we need some visualization tools that may be the open source ParaView or just Excel or HDF5 view, which to visualize HDF5 files, or our internal processor display MICRESS. Then we need quite a lot of other data sources, especially for thermodynamic and diffusion data, but also data for interfacial energies or per phase properties, which can be generated by small-scale discrete models. Then there is one area which is not yet really mature. There is only one player we know which looks at microstructure databases. So the idea would be to save the full calculated microstructure and make them reusable in future other simulations, for example, joining of two different materials and things like that. And from the calculated microstructures here in the middle, we want to extract also data, property data, and for that purpose there is a code we have also generated our own, which is the HOMAT, which I showed you for the anisotropic flow curves. But you can also go for virtual testing using Abacus or Digimat FE. And then there's one called VecStack, which is quite nice for fatigue. And the Dream3D is a very nice freeware to making post-processing texture analysis and things like that. At the very end, we need some communication with the external world, which is not microstructure. So these are all the macroscopic codes, like casting codes like Magma, Sigma, and there may be many others like Simufact welding, Simufact joining, Simufact forging, and so on. There may be some experimental exchange data. Volume graphics is quite well known for experimental analytics. And there may be a huge interaction with the external cloud of data, which may contain process data, machine readings, and things like that. In the very end, we need something to orchestrate all this kind of workflow. So we need something like a platform. We've got a tiny platform called MICPAD, which is essentially the driving file editor for our own software. There is, however, the recent development together with University of Aachen, which is called the XWIPMAP, the Aachen Virtual Platform for Materials Processing. And this XWIPMAP is also some other story I can tell you, and the story is that if we want to do modeling of processes and materials, we need domain experts of several domains. We need a common language and a common understanding of the overall goals. And so the ICMEC, which is an interdisciplinary team of 5 institutes at the RWTH Aachen, has teamed up to build a virtual infrastructure, which is the XWIPMAP, the Aachen Virtual Platform for Materials Processing. And the basic idea is that we have some web structure, and we've got institute which hosts different simulation hardware, different simulation software. One of them may be the MICRESS, which is ours, and one of them may be the HOMAT, which is also ours. Another one may be Dream3D, which is a freeware, or Damask, and so on, also freeware. And then we can have experts which develop the workflow, and we may have users which just perform parameter variations onto that pre-configured workflow. The nice story is that this XWIPMAP now is operational, and everybody can use it for free, so you find it on GitHub. And a paper appeared recently in a journal called Integrating Materials and Manufacturing Innovation, and you can find it online. It's open access. The XWIPMAP comprises different tools and so on. Can be used as a collaborative workspace, and it is freely available on GitHub. And just to put that all in a huge context is that there are different platforms around. One of them called is the AIDA, the so-called I do not remember the full name, but it's essentially a platform for electronic atomistic simulations, and has open source. And then there is the XWIPMAP I shortly introduced to you for the area of microstructures. And the VMAP is a development going on in the FEM community to standardize data exchange, and they also draw on a format which we proposed for the microstructures, which is the so-called HDF5 format. So this is a little bit the overview. So we developed all these platform type operations and the interoperability with other softwares in order to foster our market position, to make the software more attractive also for other users, because they can easily combine it with existing solutions. For example, the Dream3D is a very powerful tool, but also ParaView and so on. So let me talk a little bit about part B. Why did we do a commercial business out of that thing, although we were a non-commercial institution? The idea was that we wanted to generate income, but that income should not go for any stake or shareholders, but it should be used for the benefit of a sustainable development of the MICRESS code. That was the idea. We wanted to generate something like a freedom to operate, and do not misunderstand that in the sense of patents, but we just want to have some money which we could earn and which we could use to do whatever we considered as being useful and interesting. In that sense, we try to become a little bit independent, at least partly, of governmental funding. The other story is, as in contrast to many open source developments, we wanted to generate sustainability, so that needed all types of version control. It needed the increase of the functionalities over time. And we had to address quality issues which are raised by the industrial customers. So they need to go back to a specific version and to redo the simulations, perhaps also after 10 years or so, in order to demonstrate what has been done during their own development. But there's also a pain if you want to go commercial, and what you should do at least is, in a technical sense, you need something like a license system, you need something like a version control, and you need to have a test bed where you have a certain number well-defined simulation settings, which you always have to be capable of re-performing. Even if you modified your code, you should use these same tests again and generate the same results. This testbed has been done initially manually, but later it had to be automized, and also this development of having an automized testbed was quite important. In a legal sense, we have to generate something like license agreements, so we have to make sure that the people are aware that we cannot take any liability for what they are doing, that we just can offer the code on a best case effort, and cannot guarantee any validity of results, because the code is so versatile that we cannot even predict what can all be done with this code. And then we have to look a little bit to provide the end user with some experience how to operate the code. So we had to develop manuals and tutorials. We had to develop user-friendly interface. We had to provide support and training. And in my view, one of the most important things was to provide examples, because these examples always serve as a base to modify them and to tailor them towards their own needs. In the very end, you can do all this, but if you do not communicate to the world that there is something like a fantastic software around, you won't sell anything. So you had also to do something like marketing and sales. You have to set up a website, you have to do some branding, you have to generate a distribution network, and you have to deal with trial licenses and consultancy. I'm coming to that later. So the product branding, the easiest thing you can do is to make your products a registered trademark. That's even not much expensive. So we have both the MICRESS icon and also the MICRESS name are registered trademarks. And what one should do, and hardly recommend it, before you brand something, you should name check the existence of the name, because otherwise you may get into conflict with existing things, or the probability of finding you in Google will be severely reduced. So then it's also quite nice to have a meaning and a story behind an icon. I just will show you that for fun, because sometimes explaining that icon led to really to industrial contexts. I'll explain later. So essentially the MICRESS icon is based on this symbol, which is not the yin and yang, but it's the and yang, very well known from the Korean flag, and it stands for two things which are complementary to each other. It may be man and women, it may be heaven and earth, it may be bad and good, or it may be solid and liquid. And this is now the Tai Chi, or the yin and yang, and what we have in addition to this is that there are spots of bad in the good and spots of good in the bad, so they nucleate in regions of high curvature. And in that sense, this is something like a nucleation problem, and so on. And one thing we saw also in Korea, which is an extension of this yang, or taeguk, called in Korean, is the so-called samtaeguk, where you have got three things in equilibrium. You still have the blue sky, the red soil, and the yellow is mankind. What you see here is that all these angles are 120 degrees, so they are all alike. And as we knew from our solidification experiments, is that interfacial energies between two solids is largely different from a solid and a liquid. You never will get the 120 degrees. So we have selected arbitrary angles here, and they roughly form the Greek letter gamma, which is the sign used to denote the interfacial energies. Then we've got the difference in the Gibbs energies, we've got a difference in space symbolized by the gradient symbol, and we've got an evolution in time symbolized by the phi, which is the phase field parameter, but by the phi dot, by the time derivative. So the interface here is not like here directly going from green to blue or from blue to red, but there is a finite interface thickness in between, which is a characteristic of the phase field model behind MICRESS. What else you could ask is why this is a square and all the others are round. So the reason is that we solve our equations on a finite difference grid, and these things were not known at this time. So altogether we've got the microstructure evolution, which is characterized by the delta G, by the Gibbs energy, by the gradients in the concentration field, and by the phi dot, by the evolution of the interface. So next step, if you want to become if you want to enter the market with your software, you have to build up and to keep alive a global agent network. So the good story we had is that there was already a network from Thermocalc software, and actually all the customers from Thermocalc software in the long term might become interested in the MICRESS as well. So we could build up on that existing network, and we have to maintain it by visiting the people from time to time, giving them support in their sales activities, and so on. So meanwhile, we've got a network around the world which is necessary for that kind of specialist software, so you will not be able to be kept alive just by sales in Germany or in Europe, so you must have a global market. And so we have that agent network all around the world. And meanwhile, we are installed in 20 countries with the share, the biggest share being in Asia, and then followed by Europe and the US. And the rest of the world is by 5% roughly. We did some video publications and video tutorials which are available on the YouTube, and it's also very important to have these kind of public media and have be present in this kind of things. And it's also very valuable to train people on the code before they really start to work on it. About training, so we have to provide, or we are very happy to provide training courses at least once a year, in the recent years twice a year in Aachen itself. But meanwhile also our agents, for example, here in China, they do training courses in the system. And also what is very nice in a strategy is sponsoring the different events, because then you get network connections and web links onto these conference websites. In the very end, we've got something we can call success, and the reasons for success from our perspective in some sort of summary is that we have a modular software concept where you buy only those functionalities you really need, including a certain basic module. We've got free post-processes and free examples, so everybody can expect our results for free, especially students and education. We've got that strategic cooperation with Thermocalc software, which allowed us to use their agent distribution network. We've got an adequate pricing structure, temporary and permanent licenses for universities and for industry customers. We have decided not to issue test licenses, at least not without training. The reason for that is that people just trying to exploit our code will be lost because it's too complicated if you have no guidance in using it. And so we require people willing to have a test license to have a training first. Then we have regular releases about once or a year or once in each 1.5 years. The basic requirement we have to ourselves is that we always generate new functionalities and not just releases with some bug fixes and things like that. The recent developments turn to integration interoperability with other codes and ICME type services, and we do high-level consultancy for companies willing to buy the software. But not knowing what they get. So in that sense, we often do a study which is really dedicated to the specific user solving a problem of his interest. And as I told you before, we've got a highly experienced team of people working with the code since 20 and more years. Customer relations, we've got a good reputation. Important in the very beginning, I showed you the experimental background and expertise, the integration into the phase field science community, integration into users community and industry, strong collaboration with University of Aachen. We have a recognized translator role for several commercial challenges, and what we experience is a market pull situation because we are somehow the only commercial provider for that kind of code. And the focus, meanwhile, is of our work is to make that code useful for users, so we focus on the functionality rather than on the underlying model. And meanwhile, a number of highly interesting results has been generated and disseminated by our customers. So we have something like a snowball system where the news about the value of that code starts to spread around the world. As I indicated, the current development and the future development will be going towards simulation platforms and interoperability. And this summarizes my talk. Let me thank you for your attention. So I talked a lot about MICRESS. There is that other tool I did not talk about, which allows to extract effective properties from MICRostructure, and I talked a little bit about the XBIP map, and that finishes my presentation. Thank you very much.